in here today?
No, yeah, she is. She was here at 9.
Okay.
I don't know. She didn't really talk. She had her head down like a little man.
Okay.
Big class.
All right. Yeah, it is a big class today. All right, go ahead and get your notes out.
I have an overview library.
All right.
No. Actually do. It'll be good money. Oh my god.
And today,
Yes, we do, for once.
Is it canceled yet?
No,
No. I'm supposed to wait for the rest of the day.
it's not gonna be, they would already canceled it.
Emily, can you hear me?
Yes.
Yes.
Okay.
Why does it matter?
I could read from mine.
Oh,
Oh, it's old.
yeah, sorry, is it home or what?
Away. At London.
Oh,
Tomorrow's home.
where's that page?
All right, go ahead and get your formula papers, your calculators, scrap paper.
Oh, I need to, I'll go here.
That's your.
And so, you know, so-
Sorry to see you. Kind of late.
Mr. Sellers said, no, Mr. Gabriel said that you, if you don't do it,
Yes.
I'm actually you while you're doing, you see my phone?
because I was waiting for him to show us.
Oh, the red one?
Yeah.
Why? Why didn't you use this?
That's really good.
Well, obviously it's closing.
Yeah. I forgot it. I'm gonna grab it now.
All right, so today, well, first of all, we were doing the concentrations yesterday, and do you guys have any, does anyone have any questions on that?
Nope.
Are you guys comfortable with it, or
Yeah.
do we need to do more examples of it?
We're good. I'm good.
Good.
Oh, you're good? Emily, how are you doing?
Thanks for asking.
I'm good.
You're good? Okay, so let's do this. Let's go ahead and go into dilutions then. Actually, this is like the last section of this chapter here,
Then we move into trigonometry or whatever it's called.
stoichiometry.
Trigonometry. Yeah. Wasn't hot. I must have.
Okay,
Hopefully it's not too complicated.
It sounds complicated.
and it's, okay, so first of all, let's do this.
Let's look at it.
When you look at the formula for calculation for molarity, okay? A molarity is a mole per liter. How do you rearrange this so you solve for moles?
L times M equals MOL.
Because you have to get rid of
Let's go.
So moles is equal to the molarity times the liters, okay? Now, when you're measuring molarity, that's a measurement of what?
It's something to do
it.
with.
Isn't it mass per liter, moles per liter?
That's the unit of it. But it's like, if I ask, if you're measuring something in miles per hour, you're measuring what?
How fast?
How fast, the speed of it, okay? Molarity is a measurement of what though? Was it? It says, it is a solution, but what of the solution?
The,
So.
yeah, now.
The concentration.
Yeah, that one.
Okay.
Yeah,
It's the
yeah.
concentration of the solution
I was
here.
gonna say that next section.
So sometimes what you'll see here is, instead of, because molarity is a unit, but what you're actually measuring is the concentration of it. Okay, so I'm going to put C down. When you're measuring liters, that's a measurement of what? Volume. So when you're measuring moles, it's actually you measure the concentration times the volume, which is a molarity times the liters. Now, keep this in the back of your mind right here, because what we're going to be dealing with here is basically working with this. And also, take a look at your formula papers. Take a look at this, and flip it over to the back. If you look at it up here on the top, you're going to be seeing, if you notice up here on the top of it, it says like M1 V1 equals M2 V2, or C1 V1 equals C2 V2. Okay, this is where that's going to be coming into play here. Okay, so we're looking at C1 V1. What we're actually measuring are moles of something. Okay. Now, the way that you go about doing a dilution is that here. So you pour the correct amount of solution to be diluted into a volumetric flask. You pour in enough solvent, which is typically going to be water here. So you almost or partially fill up the bulb within the flask. And then, right now, you swirl the flask to mix the solution, and then carefully add enough solvent to the correct volume. So let me show that to you, and that process here. And then I'm not sure how much you'll be able to see back here, but if not, Tom can sit there and entertain you. All right. All right, so if you look back here. So let's say I'm making a solution, and I'm just going to use some of the salt here. Now, normally, you would use something which is called a volumetric flask. This is a volumetric flask. The word metric means to measure, okay? Volumetric literally means what? Measure volume. Measure volume, okay? Now, for these volumetric flasks, one thing you'll see here is there's a little ring up here on the top. You guys see that? Okay. That ring right there is a marker. Sorry, I can't see if you can see this or not here. A little ring right here. And if I bring this situation, this is a 500 milliliter flask. If I bring the volume up to that level, I have exactly 500 milliliters. Right? So these flasks are typically used for doing dilutions or if you're dissolving something. Right? They're not used for mixing chemicals together in here. So let's say I want a certain concentration of salt water. Pretend I weighed out the salt. And now I'm just adding that salt to it. But the problem is when I put something inside of here and dissolve it, typically you have the salt inside of here, you pour in a little bit of water, and you swirl it around. Okay? Now I add some food coloring here just because so you can see, because if it's salt and water, you won't be able to see anything what's going on here. This way we can visually see what's going on. Especially if we're diluting something down. Right? So most of the salt is dissolved now. So typically, I'm going to have a little more food to this. Make it very blue. Nice and blue. Okay, now, the thing is, you partially fill up the ball and you swirl it around. Okay, you don't do this when this thing is filled up or filled up most of the way. When it's inside of the bulb here, this allows you to be able to swirl it around and be able to mix up the stuff. And then you add a little bit more water to it. Now, typically, whenever you're doing this, you will not be using tap water. But I'm doing this just for demonstration uses here. Again, swirl it around, get everything mixed up. And then go ahead and fill it up most of the way. Bring it up close to the line. Now, Then, at this point, you use your rinse bottles, and you bring it up to that line. Okay, so now I have a certain concentration of salt water. Okay, and just keep going just so we can visually see what's going on with that. Okay. So this is my starting solution. Sometimes they call it the stock solution, sometimes they call it the reagent solution. Then, all right, next thing. Okay, the solution can be made less concentrated by diluting with a solvent. Now, here's the key part. The number of moles of solute does not change when the solution is diluted. The number of moles of solute before dilution equals the number of moles of solute after the dilution, or the moles before equals moles after. This goes back to this, what we just wrote up here on the board a little bit ago. This back around. So when it says moles before equals moles after, that means, I'll write this down here, that the moles before equals moles after. Oh, so the mole is equal to the concentration times volume. You can say the concentration times volume is equal to the concentration times volume. But to indicate before and after, sometimes they use like initial or final or 1 and 2. Personally, I kind of prefer using 1 and 2. So C1V1 is equal to C2V2. Okay, basically this equals moles, this equals moles. So the moles before the dilution will equal the moles after the dilution. Okay, now let's switch back to the screen here.
Pardon the interruption. I need the following students to report to the office: Bridget Bays, Kevin Spears, Morgan Welch, Rebecca Kaufman, Alyssa Henthorn, Jake Smith, and Riley Hunter. Thank you.
Hopefully it's not more people going home. Okay, so look up here. So if you look at this, how many dots are in that that diagram?
12.
Or how many?
Quick math.
1 dozen. Okay. Now let's say a dozen is the same thing as a mole, and this is a 1 liter container. So I have 1 mole and 1 liter. Okay. So 1 mole per 1 liter, that's also called 1 molar. Can I follow with that? Okay. Now, if I were to take this, so this is my moles, and I increase the volume, what happened to the moles?
They stay the same.
They stay the same. What happened to my volume? My volume got larger. So now I still have 1 mole, but now I have, let's say, 2 liters. So when I went from 1 liter to 2 liters, I doubled the volume of this here. So my concentration would go down by half. So now it's a half a molar concentration. So if you notice here, the one thing to always remember here, whenever you're making a dilution, concentration always goes down, volume always goes up. Now, if you think about it being, or if you're making Kool-Aid and it's too sweet, how do you make it more diluted?
Water in it.
Or more water. You don't change the amount of sugar that's in there. You just basically are spacing it out a little bit more. And so the same thing is happening with this. So by going from, back up here, now we had 1 mole and 1 liter. If I double the volume, the total number of moles remains the same. I just increased the volume. Therefore, that would have an effect on this concentration. So it went from 1 molar to half a molar. Does that make sense? Okay, now, this part's going to require a little bit more thinking here. So the number of moles always remains the same throughout this solution here. So this is where that equation, C1V1 is equal to C2 times V2. Some students in some schools here, they end up using like M1V1 is equal to M2V2. So M stands for molarity. And it's the same thing. You can do it multiple different ways here. All right, so let's say you have your stock solution. The stock solution is your kind of parent material, and it has a 2 molar concentration. I have 1 mole and a half a liter, so that's a 2 molar concentration. And I pour some into another cup. I know, amazing graphics. Now, when I pour it, simply pour it into another cup, what happens to the concentration?
It goes up. On that way, up on the other one down.
Stay the same.
Ow.
So think about this. If you take a taste of a drink directly from the pitcher, does it taste any more or less sweet if you pour it into a cup?
No.
No, that's all you just did. You just poured some of it into a cup. So the concentration still remains the same amount. Or if I were to have you guys, and I told you guys spread yourselves out evenly within the room. So right there, away from the walls and also away from each other. Okay, and then all of a sudden I put a line and cut a wall down through the middle of the room here. You still have the same amount of space. The concentration of people will still remain the same. The room has been cut in half. The number of people in the room has been cut in half, but the concentration still remains the same amount. That makes sense? Okay. So simply by pouring it into another container here, I still have the same number of particles, or I will have the same concentration as the original material. All right. Now, if I bring the volume up, if I add more water to it, then the particles get further apart, and that's when the concentration goes down. But the process of adding more water to it does not increase the number of particles within it. The concentration, or the moles remains the same, just the volume has gone up. Okay, so when the volume goes up, the concentration goes down. Okay. Does that make sense? Okay. So let me demonstrate back here. Is this possible to zoom in? Let me try something here. Give me 1 second here. Yeah. Try a few things here. Here. Okay. I don't think I can zoom in. Settings. I don't think I can zoom in. I'll try to bring the stuff up close to you here. Okay, so let's do this. All right, if you look back here in the room here. So I have a very blue solution, okay? And it's almost black down here at the bottom of this. Now, let's pretend this is 10 molar concentration, okay? And so what I'm going to do is I'm going to take some of this, and I'm going to pour half of it into another container here. And measure out. Now, I poured half of this stuff out. What happened to the concentration? Nothing. Okay. So here's my stock material. I'm going to get down here. And I'm going to pour this one into here. Okay, now, once again, so this is my, so So this is the parent material, this is the stock material right here, right? This is what I'm gonna be diluting. But you tell me about the concentration of it right now. It's gonna be the same thing here. So if this is 10 molar, this is also 10 molar. Now, there's a certain number of salt particles within here, all right? Then what I'm gonna do is I'm gonna add some water to this. I should fill it up. Just a little bit. And close enough here. Now, what happened to the concentration of this? Went down. And if you look at the color, you notice it's a little bit lighter. It's still pretty dark. But it is a little bit lighter now, especially if you hold up to the light, it's a little bit more noticeable.
Yep.
Okay. See that, Emily? So this is the stock material, and this is what I just diluted. Okay, so the thing is, I poured half of it into here, and I doubled the volume. So if this was 10 molar, this should be about what? 5. Should be about 5 molar. Okay, now I'm going to do another dilution. I'm going to pour a bit into here. Yes. Okay, now, so this is now kind of like the reagent material. This is 5 molar. What's the concentration of this? 5 molar. Still, it's going to be 5 molar. Now, put this down. I'm going to pour this into a 1 liter. This is what concentration? 5 molar. Okay. So right now, again, there's a certain number of particles within it. So there's a certain number of moles. Okay. Now I'm going to take this and add some more water to this. So now, this was 5 molar. What happened to the total number of particles salt that was in here?
No, it stayed the same.
Stays the same. So before I added water to this, there's a certain number of moles of sodium chloride in that. After I add the water to it, it's still the same number of moles. Okay, so the moles before equals the moles after. But what I've done now is I now gave them more room to move around. So I still have the same number of particles, but now, originally they were all down here, but now they're all spread out through here. So the concentration has just decreased in the process by increasing the volume of it. Okay, so if this was 5, and now this is 4 times greater.
20.
1.25. So this now has about 1.25 molar concentration, but that was 5 molar. So if you look, the differences between them. So this is our 10 molar one. Okay. So this one is half the concentration as this one. And this one is 1/4 the concentration of this, but 1/8 of the concentration of this one. That makes sense? This is the 140 here. Now, typically, whenever you're making a dilution, you will be using like one-inch glass, graduate cylinder, something like this, or sometimes you might be using something like this. Typically, in Chem 2, we tend to use these a little bit more. You guys ever seen these before? Okay. This is a micro pipette. Yeah, it is kind of fun to play with here. What this does is it measures volumes in microliters.
Pardon the interruption. I need the following students to report to the office. Frank Artis, Owen Barker, Brendan Falk, Hunter George, Braden Blade, Hayden Morse, Jared Ringler, Mason Ringler, and Matthew Bolt. Thank you.
Someone else tested positive, that's why.
Just say something.
What's that again?
Someone else tested positive, that's why they're going down to the office.
Uh-huh.
A bunch of the day or the kids.
Ay, ay, ay. Are you following along with this, Emily?
Yeah,
Okay. Can you see the flash?
yeah.
Okay. Anyway, we'll show you guys here.
This is the small, that is it.
Yeah. So this here is it's called a micropipette, and it measures volumes in units of, and you can see that in that, in units of a microliter. You guys remember how much is a microliter?
Very small. Very small.
So deci is 1/10, centi is 1/100, milli is 1/1000, micro is 1/1,000,000.
Yeah.
So this will measure in units of millionths of a liter. So right now I have this set for 1 microliter. So if I were to siphon out 1 microliter from this part right here. See that right there in the tip? 1/1,000,000th of a liter. So if you want to fill up a liter with this, you would have to do that 1,000,000 times.
Yeah.
Show you here. I don't know if you can show this. Let's see here. Come on now, focus. It's kind of hard to see, but there's a little bit of solution right here on the tip of this. So I can see it. Right about there. It's right about there. That's 1/1,000,000th of a liter. And then whenever they're making a dilution, take 1/1,000,000th. I know the concentration of this. I can take 1/1,000,000th of that, put it into here. Now I just deposit a little tiny drop right here on the side. So I know the concentration of that little droplet. I can fill this thing up and have this diluted down. Now, we don't have any equipment here at the high school that will measure that. At the college, they do. Matter of fact, this is what they commonly use when they're measuring stuff here. That you can measure stuff. There's equipment that will measure that concentration when I dilute this thing down. So we'll have millionth of a liter. Amazing, isn't it? All right. Tell you what, let's go ahead and do one of the calculations here. Let's see here. Actually, we'll do the example calculation here. All right, so you're trying to prepare 100 milliliters of a 0.4 molar magnesium sulfate from a stock solution of 2 molar magnesium sulfates. Okay. Now, it's already set up kind of for you here, but I still want you to kind of go through the process of doing it here. So to prepare 100 milliliters of 0.4 molar magnesium sulfate, that's what you're trying to make. Okay, that's your end result from a stock solution of 2 molar magnesium sulfate. If it's a stock solution, that's what you're starting off with. Okay, so let me And let me show you how to go about an easy way of setting this up. Okay, so it goes back to this. So let me erase some of this. So what I want you to do on your paper, write down before equals after. Before equals after. Okay. Now underneath before, put down C1 is equal to D1 is equal to. Same thing over here, under after, put down C2 is equal to D2 is equal to. Then you just plug in the information. So you're trying to prepare 100 milliliters of 0.4 molar magnesium sulfate. That's your after. That's what you're trying to make in the end. So for the 100 milliliters, so we'll put 100 milliliters over here. And 0.4 molar over, no, yeah, 0.4 molar over here. And you're starting with a stock of 2 molar. So that's your C1. The question is how much you have to take out to prepare that solution. Okay, so this is you're trying to find out what volume you have to take out in order to prepare the solution here. So it's just a matter of plugging it into C1 D1 is equal to C2 D2. You just plug the numbers into it. It's basically just a proportionality. So C1 is 2 molar. D1 is unknown.
Yeah.
We'll get you guys got up.
We won't be back until next week probably.
Okay.
We won't do that until Monday. Yeah. I gotta pick up my paper airplane now. Gosh dang it. Yay, 2-person class.
Yeah.
I'll have fun now. Moving my table still phone. Real, I still move my table. Yeah.
We'll get you guys caught up here.
Alright.
I'll post this up on the board later on.
Okay.
Maybe we should go home or we.
Yeah.
No, this is not enjoyable.
Mhm.
Not at all.
Nope, it's not.
All I wanted to do was play baseball.
How many people are your baseball team?
Everybody.
Everybody.
Well, not everybody, but everybody. Have a good day.
Yep, you too.
Oh.
This stinks. All right.
You have a class.
Hmm?
So you do still have a class.
I do still have a class, so
Well, we're going down.
yeah. So, all right, so concentration is 2 molar. D1 is unknown. C2 is 0.4 molar. Now, before you put this other one in here, technically, whenever you're doing this, this should be in liters. Okay, so let's go ahead and convert this into liters here. 100 milliliters. So 1 liter is equal to 1,000 milliliters. So milliliters is going to cancel out. So 100 divided by 1,000 is 0.1. So 0.1 liters. I'll put that up here. 0.1 liters. So this is what you're trying to solve for, V1. So how do you solve for V1?
Two out more with the other side.
Combine down to 2 molar. Cancel out. And then over here, molarity cancels out. So V1 is equal to 0.4 times 0.1 divided by 2. 0.02. Right? Okay. 0.02 The units for that would be, unit left over would be liters. Now, because a lot of equipment do not measure in liters, most of them measure in milliliters, so let's convert that into milliliters. So 1,000 milliliters is equal to 1 liter. Liters might cancel out. 20.
Yeah.
20 milliliters. That's your answer right there. Now, I'm going to diagram what exactly this means here in a second. But this is commonly, whenever I'm making a dilution, this is one of the common things I have to do here is like, okay, I'm preparing a lab. I need a certain concentration and I need a certain amount of it. The material I'm working with has a certain concentration, but I need to get it diluted down to something that's less. So the question is how much do I have to take out of it to give me that concentration? So what this means is what I would recommend doing is drawing this down. Diagram, that's what this means here. All right, so what's happening here is you have a stock solution. A stock solution has a concentration of 2 molar. What this means is you have to pour out this 20 milliliters. It means you have to pour out of it 20 milliliters into another container. So I have 20 milliliters poured into here. Now when I pour it into it, what's the concentration of this? Still going to be 2 molar. That means there's going to be a certain number of particles that's within there. Okay. Then you're going to bring this up to 100 milliliters. So then I'm going to take add some water to this, and now bring the volume up to 100 milliliters. You see that? Yep. Okay. And when I bring the volume up, what's going to happen to the concentration? Concentration will get less. But what's going to happen to the total number of particles in here? Right, they're just going to get further apart. Still going to have the same number of particles, they're just now going to be further apart. So now the concentration of it is going to be 0.4 molar. So I went from 2 molar to 0.4, and at the same time, 20 milliliters to 100 milliliters. Does that make sense? Mm-hmm. So if you look at the total moles of particles in here, that equals the same number of moles of particles I have over here. So the moles before equals the moles after. You guys follow with that? Mm-hmm. Okay. So this is, I can't tell you how many times, even with the college students here, sometimes, especially when they first start learning how to do a dilution, they can do the calculation. But I like to draw it out because all of a sudden they'll get to there, and all of a sudden when you have the actual chemicals and equipment right there in front of you, they sometimes freeze up. And I was like, I don't know what to do. Okay, so this is basically what this means here. When you're doing this calculation, when you get 20 milliliters, that means you're pouring out 20 milliliters, start with 20 milliliters in here, then you bring the volume up to 100 milliliters. Okay, the one thing, kind of a good way of checking your work is if you look at when I put the answer inside of here, so this is 20 milliliters or 20 milliliters, 0.02 liters. If you're making a dilution, the concentration should always get less and the volume should always get bigger. If you ever have a situation where that's not happening, so whenever you're comparing your before and after, so the before should be more concentrated, after should be less concentrated. The before should be less volume, after should always have a larger volume. If you ever end up where that doesn't happen, something went wrong. Right? Does that make sense? Okay. So let's try another one here. All right. That's what we just did right there a bit ago. So let's try this one. A solution is made by diluting 150 milliliters of a 0.12 molar ferric nitrate solution with water to a final volume of a half a liter. Calculate the molarity of the ferric nitrate in the diluted solution. Okay. Now, what the material is does not matter. So it doesn't matter if you're talking about salts, ferric nitrate, hydrochloric acid, anything of that sort here. None of that matters. What matters is the volume and the concentrations. Okay, so again, when you're looking at this, you have to sometimes figure out when it's being worded here. Sometimes it's difficult to figure out what is it before and what is it after. So before you start diluting, after is after you're done with the dilution. So the solution is made by diluting 150 milliliters of 0.12 molar ferric nitrate solution with water to a final volume of a half a liter. Calculate the molarity of the ferric nitrate in the diluted solution. Well, right there in the very end of it, calculate the molarity of the ferric nitrate in the diluted solution. It's asking for what is the C2. To a final volume of 0.5 liters, that's your B2. And it's made by diluting, and it's telling you what you're starting off with. So that's your starting material. Okay, so look up here. So let's put the information in here. So it's made by diluting 150 milliliters. So that's B1 of a 0.12 molar concentration to a final volume of a half a liter. Okay. And it's asking what is the new concentration. So we're trying to solve for this part right here. Now, one thing too is if you look at your units, milliliters and liters, we need to get these two so they're matching. You'll get a weird answer if you try doing you didn't do that. Typically, it's best if you go make everything liters. So let's convert this into liters here, 150 milliliters. 1 liter is equal to 1,000 milliliters. Milliliters are going to cancel out. So how many liters is that?
0.15.
0.5. 0.15 liters. All right, so now we have our C1, we have our V1. We don't have our C2, but we do have our V2. So we're trying to solve for C2 this time. So let's go ahead and plug in the numbers. So C1 is 0.12 molar times V1, which is 0.15 liters, is equal to C2, which is unknown, times V2, which is 0.5 liters. So we try to solve for C2. What do you do?
So you bring the 0.5 liters over to the other side.
Calculating the concentrations are pretty easy. You're always making everything is in the numerator and just getting rid of one of the other variables here. So over here, half a liter will cancel out. On this side, liters will cancel out. So C2 is equal to 0.12 times 0.15 divided by 0.5.
So 0.036.
And the units for that would be molar. So for molars here. So that would be the end concentration of it. So this is your answer. So it'd be 0.036 molar ferric nitrate. Now, again, let me diagram this. So what that means is this. We're starting off with a 0.12 molar concentration. Just thought. And certain amount of material in here. You're pouring out 150 milliliters. Out of it, and put it into another container. And so you pour out 150 milliliters of it. When you pour out 150 milliliters, what's the starting concentration? Still going to be 0.12 molar. Okay. That means there's a certain number of particles within there. Then you're diluting it. And when you're diluting it, you bring the volume up to a half a liter. And so you still have the same number of particles, they're just now further apart. And the concentration of it is now 0.036 molar. That make sense? I think that's where we're stopping for today. All right. Emily, do you have any questions?
No.
No? Okay. We'll just continue this on tomorrow. Are you able to see the stuff up on the board?
Yes.
Okay, that's good. If you have any questions on the stuff later on, let me know.
Okay.
All right.
Thank you.
Have a good night.